So this is the title that Randall gave me. And so hopefully I will get to say something about this, but there's a few other things I wanted to talk about as well. There's also more in the copy of this talk that I expect to get to. So I added some things just for general information, which people can read later. Okay, so I always like to start off with this plot. This is partly for career satisfaction, but also because it tells us something interesting about our field. And this is refereed papers containing the word expec in 2-year bins for this millennium. So you can see at the beginning, we were running about 250 papers a year. And over the first decade, there was an increase up to a bit over 500 papers a year. And I think that's a consequence of Chandra and XMM, and also to some extent Suzaku. And then things sort of flattened off a bit in the early teens, and now it's running up again since about 2016. So part of this, I think, is Newstar, which has been pretty successful, but also this is the rise of Chinese and Indian X-ray astronomers. Certainly from the questions I get, and also just looking at some of the papers being published. And I think in the last year, the Chinese Academy of Sciences in Beijing was one of the top 10 addresses in expec papers. So thank you to everyone in Asia, particularly for staying up, if you're staying up late to watch this. So it's actually over 11,000 papers now, over 400,000 citations of these papers, and a collective H index of over 200. I can't quite decide whether that collective H index is good or bad. Someone else can think about that. Okay, just a summary for what's happening with XSpec. We had a new version that came out in March. Generally, we try and do one release a year, but as most of you know, I think it's easy to get additional local models. There's also lots of local models which rattle around without me knowing about them, so it's sometimes interesting that we get questions about models that we know nothing about. HereSoft now includes GSL, so you can use any of those routines. And this is sort of an important point. Please do not use numerical routines in models. Numerical recipes routines are copyrighted, so we're not really supposed to be distributing them. And in fact, we've been going through trying to eliminate them from all our code. We'd eventually like to have everything on GitHub, and part of that is making sure that we're not violating any copyrights. There are other interesting issues with that, which if this was a real conference, you could ask me over a beer. There'll be a new release of HereSoft in a couple of weeks. This is mainly for Newstar. This will just be a patch level release for terms of XSpec and PyXspec. One thing we've noticed recently, which this is a word of warning for Mac users. As you know, Apple is switching to their own silicon from Intel processors. So the new version of Xcode version 12, which supports this, produces universal binaries. And we've done some initial testing, and it looks like if we use Xcode 12, there's going to require a lot of changes to our code. So other people may see similar things. Possibly we're just going to fall back on recommending people just use GCC rather than the built-in Apple compiler. Generally, if you're not a member of the XSpec Facebook group, I recommend you join. We're running about 940 members now. If you put in an application to join and I don't actually let you, then please let me know, because I do try and maintain some quality control on this. So, but if you have a pseudonym or something, so I can't find out who you are, that might be difficult. Okay, I wanted to also say something following on from Yella about binning. So something we did in the last release was to allow this sort of multiple response thing. The reason is if you go to the full CRISM resolve matrix, you've got 60,000 energy bins and 60,000 channels. And calorimeters like CCDs have a response down to 0 energy. In other words, if it's a 6 keV X-ray coming in, then most of the response is very tightly around 6 keV, but there's this long tail. So you end up, the full matrix is over 7 gigabytes, which is obviously totally impractical. However, most of this response is very smooth, it's long tail. So what we've done, and this is in collaboration with the CRISM Resolve team, is to split the response into the high resolution bit and the smooth bit. So the high resolution bit is at the full 60,000 by 60,000, but it's a sparse matrix. It's just a few diagonals for the main peak and the escape and things like that. And then we've got a 1,000 energy by 60,000 channels triangular matrix with a long tail. So what happens in XSpec then is the model is calculated on these 60,000 energy bins. A copy is binned up to 1,000 energies. They are each multiplied by the appropriate matrices and the results are summed. And the testing on this, which was mainly done by Edmund Hodges-Clark, found that we get order of magnitude speed ups and correspondingly order of magnitude decreases in the size of the response with no loss of accuracy. Now this is all in this latest version of XSpec, this is all handled automatically. The response file basically has 1 E-bounds and 2 matrix extensions. Now in principle, we could also extend this to bin on channels so as to make our triangular matrix even smaller. But then there's sort of an issue about then how you expand out to the full number of channels. But also if you're using Yella's optimal binning on the channels, then that's helping you on that as well. Okay, this is something that Jeremy Sanders actually sent me a couple of weeks ago. And it's a different issue with spectral. This is very low resolution spectroscopy. In fact, it's continuum spectroscopy, but it has an interesting problem. So Jeremy is part of the eRosita team, and they're interested in measuring the temperatures of tens of thousands of clusters, some of which won't have that many counts. But they need to know whether there'll be systematic errors, because they're then going to go on and use this for cosmological determinations. So what Jeremy did was he generated about 100,000 10 keV temperatures, and then did the fits to, and then seen what the best fit temperature was, which came out. So this is what these plots are on. Both a linear and a log plot for the fraction and the bins. And the blue, which he called the APEC default, was that was the 51 temperatures. And then the red is the APEC, which is this new 201 temperatures, which Adam mentioned, and which we've made that change actually because of getting the lines right, but it helps with the continuum as well. However, there's still some structure that shows up in these fractions. And the green line, the MECAL, which is the older specs, this is the version in XSpec which is explicitly calculating. It's not interpolating on tabulated spectra. So it's clear that even And this is 10 keV temperature, so this is pretty much continuum. So we still have some issues about interpolating on the continuum. So we'll experiment with sort of increasing the number of temperatures, but it may be necessary for the APEC model itself in XPEC to actually be calculating the continuum and not interpolating it. But the continuum is the relatively cheap thing computationally, so that would just involve moving some of Adam's code into explicitly into the model. Okay, now the stuff I was supposed to talk about. So I don't have a huge amount of experience combining high and low resolution data, so I thought I'd make myself a little toy case to play around with. So I made a fake high resolution detector with a full width half max 5 EV, and then a fake low resolution detector with a full width half max 100 EV, but with 10 times the effective resolution. And then I just took a single Gaussian line and a background, and I looked at a couple of cases of a 30 EV signal line and a 5 EV signal line. So this was with the 30 EV signal line. So this is the confidence contours for line energy and line sigma. And the red dashed contours were just for high resolution, and the blue solid contours were then doing them both. So clearly, in this case, including that lower resolution data is a big help in terms of constraining the contours. And maybe that's not that surprising because a 30 EV signal line is going to be comparable to the resolution of the detector. So, but then when I switched to a 5 EV signal line, in this case, this is the same scheme with the red dashed lines being high res only and blue solid lines being with both of them. In this case, it doesn't really seem to gain you anything by including the lower resolution data in terms of at least of measuring the line energies and the line sigmas. Now, what you might also be wondering about is the annoying thing about this is I now can't see the top of my screen. So what I wanted to go to was this one. Okay, so this shows the line normalization, and in this case, and this is just the one-dimensional delta C statistic changes. So and the sort of magenta line, I think, going across is at a delta C of 2.706, so 90% confidence. And clearly, including the low resolution data helps you a lot in getting the line normalization right. Just going back to the previous one, this was just an experiment where I used Yeller's optimal binning to see what it made any difference. And in this particular case, it doesn't, so, which is both good and bad. Anyway, so the things that I worried about, what could possibly go wrong. In the low res data, you've got obviously a lot more counts than in the high res data. So conceivably, even if your model is correct, you could find yourself being driven into a local minimum, which doesn't work for the high res data. So I think probably, and people who've tried this can, on real data could comment. I would guess it's probably best to start fitting the high res data. Make sure that you understand what the model is from that and sort of whether you're in the right ballpark, and then you can include in the low res data, and that will probably help you tie down line strengths and things like that. If you actually have the wrong model, then indeed you can end up with a global minimum. where you're driven into something which sort of fits the low res data, but that doesn't work for the high res data. And as long as you have enough signal to noise in the high res data, you should be able to tell that, but you're going to have to find a better model. And perhaps the more complicated question is, suppose the low res data has calibration problems, then you could sort of get driven into a fit which gives the wrong parameters. And so I tried another experiment. I said, okay, suppose I say that my low res data, I have the gain is wrong by 0.1%. And the chair of this session can comment on that, but then, that's a really optimistic assumption that you can get the gain calibration that well on something like a CCD. And then this is the 30 EV sigma line, and here the blue is the original. I tried to keep a consistent schema, and then the red is now with this gain shift put in. So you can see that there's a sort of significant shift on the best fit energy. So by including this low resolution data, you could be actually pulling the measured line energy away from that which maybe just the high res data on its own would find. So I think that's perhaps something that one needs to be a bit careful about. And then when I go to the 5EV, again, there's a slight shift, but it's not as big. And in fact, if you look at the x-axis numbers on there, this is defining the line energy quite well. So again, as long, the sharper your line is, the less you have to worry about it being pulled off by slight problems with the gain calibration of the low res data. And hopefully you might be able to tell that this was happening if you saw from the residuals. Okay, so according to my timer, I've got about a bit over 2 minutes left. This was just then looking at this normalization again and having this slight gain problem on the low res data. It doesn't actually make any difference. So you'd be fine on that. Okay, since someone actually asked a question during Yella's talk, in fact, I'm expecting that I'm now going to get questions about specs after this talk. So I've got this C++ library called here SP, which is also a Python module. It allows you lots of manipulating spectral responses and table models. And then built on top of that, there's a new set of tools, which we're slowly using to replace some older versions. And in particular, is FT Group PHA, which is a replacement for Group PHA, has a lot more options on binning, including the optimal binning scheme. So anyway, let us know if you spot any problems with these. We're obviously testing new ones against old ones fairly carefully, but before switching things out totally. And finally, this was just notes about what was in the new release. Again, as Adam mentioned, we went from 51 to 201 temperatures in the AtomDB files that we have. Anyway, there was you can find out about why on the AtomDB. Some of the internal handling statistic was improved. You can have a different fit statistic for each spectrum. And there's obviously only one total test statistic. And then there were a bunch of new models, including got round to including Leah's dust extinction models. There's a new thermal optimization convolution model from Andrzej Jarsky's group. And then the Becker and Wolf and the Nielsen models were ones we were able to include because we have GSL now. in there. And my timer says I have 5 seconds left, so I will stop there.
All right, thank you. That's what my timer says too. Thanks very much. And I completely agree with your assessment of the importance of calibration when you're simultaneously fitting high resolution and low resolution data. And this is something that will be important for CRISM, which has a high resolution and low resolution instrument on it, as well as Athena. If you want to do simultaneous fitting, you need to understand the calibration systematics, how they differ between those instruments. All right, so we are officially out of time, but we have a couple of questions that I'd like to answer if you will bear with us. So the first one is from Lydia, who asked a question. I don't think this is directly related to what you addressed, but is directly related to what XSpec can do. And her question is, what would be your advice for modeling of spectra of hydrogen and helium-free objects? So things such as Wolf-Rayet WO type stars using thermal models in XSpec.
Right, that's actually a question which has come up in terms of supernova remnants and stuff. I'm tempted to bounce this over to Randall or Adam, because I know we've had discussions about this.
Okay, I can jump in. Essentially, I mean, you can use the existing VV models, which let you set the abundances of hydrogen and helium to 0. And the spectral shape should be fine. The problem is the norm becomes it means a very different thing. So, because that's based on assuming electron to hydrogen ratio, which no longer applies. So you need to recalculate. If you're going to try and estimate how much gas is emitting, you'll need to do something to recalculate your actual electron abundance effectively. But the shape should be correct if you use the VV, APEC, or NEI models. Yeah.
Okay, great.
Okay.
And Randall posted a link to a paper in the chat window, which maybe we can transfer that to Slack so that everyone has access to it. And I see that Keisha has posted on Slack just a reminder to Keith to please include in the next TIASoft patch or distribution the option to include activation of the min channel and max channel options for group type equals opt choice in FT group PHA.
That will be in the release, which is coming out in a week or two.
Okay, great.